working? Yes.
Yeah.
Bitte?
Wann ist nochmal genau What's-Deadline?
Heute, aber ich glaube Anyone Earth, oder?
Ah, was?
Also es ist schon 20. Aber
Das ist schon heute.
schon heute, aber ich glaube AOE, also morgen früh um 11 Uhr.
Nicht durch.
Wieso? Noch kritisch.
Die erste Woche. Nee, du musst noch geschlossen werden, was noch von den Erkennungskosten haben.
Ja, gut, in der Schnee sind wir.
Was?
Das ist bei GG was eingereicht. Das ist ein AWG-Deadline.
Also ja.
Das war eine Rückzeit mit dem
So, den hat ich nicht gedacht. Oh, cool. Das ist interaktiv dann, ja?
Ja, wenn der Whiteboard-Platz wenig ist, dann kannst du etwas draufschreiben.
Womit was benutzt du? Also ne, das hat ja in
GoodNotes heißt das.
Hä?
GoodNotes heißt das Tool.
Ach, gut, okay. Das ist ja allgemein.
Do you need to put anything here?
Yeah, I have to put my email address in.
Okay.
Where's dots? Oh, it's here.
Okay, good. Thanks. On the cell phone, yes. On the computer, we can do later.
I guess we can start. Okay, hello everybody, and welcome to the 11th Winter School on Computational Geometry. I still remember the first one. Actually, I grew up with Winter School. I guess it was the first semester in master program that we started this Winter School. So I want to use this opportunity to thank Dr. Muhaddis and his team, his students, to make this happen for 11 years. Please join me to thank them first. So as you know, every year we invite top computer scientists, theoretical computer scientists with focus on computational geometry and graph to MKB University to have a crash course on computational geometry topics and their research. So this year we are honored to have Dr. Martin Nollenberg, if I pronounce it correctly, from Vienna University of Technology, and Kevin Buchen from Eindhoven University. So Martin will mostly talk about graph drawing and the topics around graph drawing, and Kevin will focus on trajectories and movement patterns. And you have the program in the website if you want to know the topic, exactly what happens, when happens. And we try to be with the schedule, but sometimes delay happens. So if there is any change to the program, we announce it here for everybody. There's a Wi-Fi connection if you want to use internet, but you need a MKB University passport for that. Please find one of the MKB guys to have that passport. So without further ado, we start with Martin.
Okay, thank you. Well, welcome. Good morning, everyone. It's an honor to be here and also to open this winter school with the first lecture on graph drawing basics and planar graph layout. So one of the most fundamental topics in graph drawing, maybe. But first of all, let me thank the organizers for hosting this for 11 years, like you said, and for me being able to be here and share some of my research interests and topics with you. So. I know this is not a very small audience, but of course you can always interrupt if you have questions. If anything goes too fast, please just raise your hand and we can slow down and I'll try to explain. So to make this interactive, it's not like I'm here 60 minutes talking and then you can ask questions, but of course feel welcome to stop me. So I want to start with graphs and the representations. Of course, we all know graphs. Yeah? What is a graph? A graph, yeah, this is how we typically describe a graph. Yeah? It's a tuple of a set of vertices, V, and a set of edges. And these edges are, of course, pairs of vertices, and they highlight the connections. So how would you represent a graph? Of course, you can use this mathematical notation and just write down sets. For example, like this. Yeah? So this is a graph with 10 vertices and some number of edges. If I ask you, is this graph planar? It's kind of tricky, yeah? Because you have to parse what's happening behind it. And probably if you would have to answer that question, you would take out a paper and a pencil and start drawing. Okay? We know other representations that are maybe useful for computers to deal with graphs. One typical one is adjacency lists. So for every vertex, you list all the neighbors. That's maybe even a bit easier to parse also for human than just this set of edges. Similarly, you can use adjacency matrices, where you just put a 1 whenever two vertices are connected, otherwise it's a 0. So this is all very well for computers. But for humans, at least if the graphs are not too big, the easiest way to understand and to get an idea of the graph is to draw maybe vertices as points or small circles or disks, and then connect any two neighboring vertices by an edge, which could be a straight line edge like done in this drawing. Can also be any other edge. Okay? So if I ask the question again, is this graph planar? I don't know, the drawing doesn't look planar, right? But that's not the only drawing. So you can rearrange that graph to have this kind of shape and drawing. And now this is a very easy question to answer, because planarity of graphs is just defined by the existence of a drawing without a pair of crossing edges. And this is a good witness. Of course, you can program your computer and do planarity testing algorithms to answer that question based on adjacency lists. But for humans, a drawing like that already shows one of the most fundamental properties of graphs. For example, you could also see whether the graph is connected. You could see what is the largest degree vertex. So many important properties you can see from the visualization of a graph. Okay, so this is all this kind of range of ways of representing a graph, and today we will focus on these types of drawings and how to compute them and properties and so on. Okay, this is the motivation slide. So why is graph drawing important, apart from being fun to get an understanding of graphs? So graphs, of course, are very ubiquitously used to model networks that come from applications in reality in a mathematical way. Yeah, so they can be models of social networks like Facebook or Twitter graphs or email connection graphs. They are used in biology for metabolic networks. They are used in hardware layout when you want to compute how a chip design is organized. They're used in software engineering for drawing UML class diagrams. You can do citation networks if you want to understand how researchers collaborate and so on. So this list goes on and on. I just put a couple of examples. This is an older graph that shows how I think different companies in Germany owned shares of each other. This was maybe 20, 30 years ago when there was one big insurance company that was basically holding shares of almost everything else. Yeah, so this was also called it's one of the economy networks here. Second one is an artistic drawing by a guy called Mark Lombardi. He's an artist from the US who died in the early 2000s. And his idea in his art was to draw conspiracy networks. Yeah? So here all these nodes would be people, like politicians or bosses of companies, and whenever there's an edge, this means that they have done business together or did stuff like that. And this became popular when I think he had one of those drawings before the 9/11 attacks in New York, and there was just a one hop between Osama bin Laden and President Bush at that time. Yeah? So that was kind of interesting and in the media for a while. This is a typical class diagram from UML, where you have different classes, and you see here the edges are now slightly different from what we've seen before. They use polygonal paths with a couple of bends, and the vertices are now boxes because they need to be filled with text. There's an example like this, which is I think a wiring diagram of some electronic device, which also is actually a graph behind it. The next one is a very big network. I don't know if any one of you has seen this. It's used. I mean, if you go to your biology colleagues, you probably find this hanging on the wall with many of them. So this is the human metabolic pathway map, drawn by hand by a couple of people, and this basically shows every molecule in your cells and how they relate to reactions and so on. This has 10,000s of nodes, but it's actually used by people to understand or to see, okay, I'm focusing on this reaction, where does it happen, which part of the cell, and so on. This is like an evolutionary tree, where you could see the different events in history when, I don't know, plants separated from animals and how animals separated among each other and so on. So this would be a tree, but drawn in a cyclic way. And the last one is, I think, a network of different diseases, and diseases are connected if they have been attributed to the same gene defects in the cell. So this would be a network that you can explore to understand different diseases and illnesses. So we do all these drawings because humans think a lot visually. Yeah? And if you want to understand a network and not just know, I don't know, graph parameters like what is the diameter, what is the node count, what is the largest vertex degree, then visualizations are usually a good way of providing some kind of structure of that graph. And these visualizations are useful once for exploring the data. So if you have a new graph and you want to understand what's going on, maybe putting it into a graph drawing tool is helpful so you can explore what's going on. But once you've found out what is special about this graph, maybe you want to communicate this. Maybe in a research paper you put a drawing of some graph that you've studied, or also in newspapers and magazines when they want to show some relationship between politicians or public figures. In order to draw all these graphs, luckily we need algorithms, because doing all this by hand for every single graph that you have is just too much work. Yeah? So we need algorithms, and in particular geometric algorithms, to draw these graphs and make it accessible to people using the data. Yeah? So this was basically the motivation why graph drawing is actually an interesting topic, and it basically forms the foundation of many network visualization tools that you find in more practical domains like information visualization. Okay, so graph drawing as a research field started in the 60s, so almost 60 years now, or 55 years, with two papers by famous computer scientists, namely William Tutt and Donald Knuth. In the same year, they published papers that basically laid the foundations of this area of graph drawing. The conference on graph drawing and network visualization started much later in 1992, but since then it happens every year, and you can go to this website graphdrawing.org to see where the symposium was held. And what's also important to know, if you go to that website, you also have free access to all the proceedings of the last 27 years or whatever we have now. Yeah? There are several textbooks now that cover different algorithms in graph drawing. I just put it like covers of these books here. The most recent one is maybe this handbook of graph drawing and visualization, which appeared 3 or 4 years ago. And this is also freely accessible online, because Tamassia put all the chapters on his webpage. Yeah? There's also software libraries and tools for graph drawing, like OGDF, which is a community-driven tool. YWorks or YFiles is a company in Tübingen, who kind of a spin-off of the university there. Gephi is a very popular tool among people, maybe more in the applied side of graph drawing. But all of those contain a lot of the basic algorithms that you can use for graph drawing. And if your task is just to get an image of a graph, then pick one of those and you'll be fine. Okay, and this is a very nice quote from Don Knuth, who was keynote speaker at graph drawing very early in 1996. But he said that he likes this field a lot because it has mathematical beauty, because there's theory and proofs that you do. The algorithms are very nice, but also the work is relevant to the world, and it's aesthetic beauty. So if you like to combine theory and mathematics with aesthetics and design, then this is a very nice field. Yeah? All right. So let's go and boil down a bit to the graph drawing problem that's guiding everything. This is some theoretical work by a cartographer called Bertin from France. And he said when you do design and maps and information design, then you have basically these 7 variables that guide how to do graphical representation. Yeah? Many of those, like color, this is not really relevant for getting the geometry of the graph. Yeah? For the geometry, the position of vertices and edges is the central problem. So when we design graph drawing algorithms, most of the time we only focus on the positioning, on the geometry of the network. And then of course you can use color and texture and size to represent additional attributes of your data, but this is not usually the algorithmic challenge. Yeah? So we will focus on this layout problem. So how can we phrase this? For now, for most of these lectures, we will focus on this called standard representation, where nodes are points or small disks, and edges are curves. Yeah, simple open curves that go from one vertex position to the next vertex position. So to phrase it mathematically, we can say, given is a graph, set of vertices and edges, and what we want to find is a drawing of that graph. We call it gamma. And gamma maps all the vertices to points in the plane, and all the edges to curves in the Euclidean plane, such that one endpoint is the point where we map the vertex u, and the other endpoint is the point where we map the vertex v. Yeah, so the standard way you would do for graph drawing. But now we want the best or a good graph drawing, so we have to define what is a good drawing actually. And usually in the literature you can split different criteria that phrase what is a good drawing into different categories. The first one is called drawing conventions, and these are hard constraints, required properties, necessary properties that you need to satisfy. And this really depends on what you want to do in your drawing. So some examples could be, please do a straight line graph drawing. Yeah, so you want straight line segments between the nodes. But you could also say, no, all the edges must be orthogonal polylines. So for example, here we have edges that maybe use staircase paths. Yeah? It could be a constraint that we have a grid drawing, so all the vertices are on integer grid positions, like in this one. Or if it's a planar graph, then the requirement could be that we actually want a planar drawing, yeah? So no crossings. The second class of criteria is often called aesthetics, because they are kind of motivated by aesthetic criteria that make good drawings, but it's used more generally, even if it's not really an aesthetic property. So this could be stuff that should be optimized in the drawing, so we can give a objective function that we want to minimize or maximize depending on the topic. This typically could be number of crossings, so find me a drawing with the minimum number of crossings. Or it could be, if you have polyline edges, minimize the number of bends, so preferably do straight line edges. It could also mean that if you have a drawing, try to make all the edges the same length, yeah, so have uniform edge length. Or minimize the area, so what is the smallest area that we need to draw a particular graph? This could be a problem. Other things are angular resolution, so when you have a vertex of high degree, or say of degree 3, then if you compare this drawing with this drawing, you probably like the one with the 120 degree angles much more. Yeah? Or if the graph has symmetries, maybe the drawing should show them. Yeah? So this is kind of a wheel graph with 8 vertices on the outer rim, and you can do this squiggly drawing or the nice symmetric one, and ideally you would want to do this. Okay? And the third group, which is not so frequently used, is some kind of partial or local constraints that could be constraints on position of some vertices. So maybe you have a group of vertices that should be together, and then a local constraint could say, okay, they should be contained in a disk of some certain radius. Yeah. So now that we have that, we can try to redefine our graph drawing layout problem using these properties. Yeah, so now the input is again the graph, and we want a drawing like we defined before, but it must comply with all the given drawing conventions that we put, for example, planar drawing. It should optimize the given aesthetics, for example, minimum area drawing. And if we have partial local constraints, then these need to be met. Okay. And now, often all these things lead to NP-hard optimization problems. So if you want to minimize crossings in a graph, this is a classic NP-hard problem. And if you put several constraints, then these criteria might even be competing. So you need to define trade-offs, like maybe you can do better angles if you allow more area of your drawing. But now you have this trade-off between smallest angle and area of the drawing. Yeah, so this would be typical things that could be competing here. Okay, any questions about these basic definitions? If not, then for today I would want to look into planar graph layout. So having graphs that are planar, how can we compute good planar drawings of these graphs? Planar graphs, I guess, are known to everyone, but this is just one slide repeating what's going on here and putting the notation. So of course, a planar graph is a graph that can be drawn in the plane without any pair of crossing edges. And if we have such a planar drawing, then it usually subdivides the plane into different regions. These regions we usually call face. And the faces are bounded by edges and vertices. And then we can speak of the degree of a face, which would be the number of vertices on that face, and so on. There's one special face, the external one, which is unbounded, and it sometimes has a special role. Yeah. Okay. So the next term that we need is the term of embedding. So embeddings and drawings are not the same thing. A drawing is something concrete in the Euclidean plane, but embedding is kind of the combinatorial topological structure behind this drawing. Yeah? So if we have three different drawings of the same graph, the question is, are they the same embedding? Embedding meaning the same face structure, for example. So if you compare the first two drawings, the only change that happened here is that somehow the positions are shifted. Maybe some edges turned into curves instead of straight lines, but you would see exactly the same faces. If you go to this drawing, it's again straight line, but it looks somehow different. And if you want to spot the difference, you can see that vertex 3 was flipped inside. And this is a different class of graph drawings, a different equivalence class or different embedding. Okay? So the first two are the same embedding, but the second one is not. And the way to mathematically structure these embeddings is by looking at the so-called rotation schemes, which means that you go to each vertex of the drawing and you collect the cyclic order of the outgoing edges or of the neighbors. And if this order is the same for all vertices in the graph drawing, then it's the same embedding. Yeah, so you can check this, for example, if you have vertex 4, the cyclic order is 5, 2, 3, 7, and here it's also 5, 2, 3, 7, but if you go here, it's 5, 3, 2, 7. So here it changed. Okay? And in order to really specify the embedding is that all vertices need to have the same rotation scheme and the same external face. Yeah, so you can use the same rotation scheme but make one of the other faces the outer face, and then it would be a different embedding in the plane. If you draw it on a sphere, then it's exactly the same. Okay, so we will look at planar graphs and planar graph embeddings. And planar graphs are, of course, very well studied in the literature. So this slide just gives a bit of background, what is known about planar graphs. So for example, the famous Kuratowski classification says that a graph is planar if and only if there is no K5 or K33 as a minor. Yeah, so the complete graph on 5 vertices and the complete bipartite graph on 3 vertices on either side. Also testing whether a given graph is planar can be done even in linear time. There's many algorithms. Maybe the earliest or most popular one is by Hopcroft and Tarjan from the 1970s. So testing whether a graph has such a drawing, that's not hard. Even we know that every planar graph can actually be drawn with straight line edges. Yeah? And this is also already known since the 1930s by Wagner, but it has been rediscovered like a couple of times. And one interesting theorem also says that a graph is a planar graph if and only if it has a disk contact representation. Yeah, so if you have a planar graph, you can represent that graph by using disks to represent vertices and edges by touching disks. So all these disks are disjoint, but they can touch. And maybe one direction is the easy one. So if you have this disk contact representation, just put your vertices at the centers of the disks and connect to disk centers if the disks touch And because this will go through the tangency point, you will actually get a straight line drawing out of this. Yeah. The other direction is a bit harder to show. All right. And we also can apply Euler's characteristic to planar drawings. So we know if we have a planar graph drawn in the plane, then it holds that number of vertices minus number of edges plus number of faces is always equal to 2. If it's a connected graph. Okay. So how do we draw these planar graphs? By doing in a way that they satisfy the properties that we want from a planar graph drawing. Or what is a good planar graph drawing? Here we go for straight line drawings, so it's clear that all the edges must be straight line edges. One of the first theorems in this Tutt paper from 1963, where he, like how to draw a graph in the plane, the one paper that basically started the field, describes an algorithm that computes for 3 connected planar graphs straight line planar drawings by a kind of barycentric layout method. But the disadvantage here is that we have no guarantee on the required area of that drawing. So there can be some edges that are very long, there can be some angles that are very small, and people then studied what is the kind of the upper bound that we need for planar graph drawings if we use, for example, grid points. So what I want to show you today is this result by Schnieder from 1990, saying that every n-vertex embedded planar graph has a planar straight line drawing on a grid of size n-2 by n-2. Okay, so n is the number of vertices, and this is kind of a small and compact grid. And the nice thing about this algorithm is that it uses different tools for achieving this, which in the beginning it seems a bit like magic. When I saw this algorithm the first time, it was very fascinating that this actually works. So the first input assumption is that we can focus on maximal planar graphs, meaning graphs where every face is a triangle. If we have a graph that is not maximally planar, then we can simply add some edges, have a maximal planar graph, draw it, and then delete those extra edges. If it was a planar drawing with the properties for this maximal planar graph, then of course the other graph is also still planar. Yeah? So if this is the graph that you want to draw, make it triangulated, add the blue edges, draw that with your algorithm on some grid, and remove the blue edges, and you have your drawing of the initial graph. Yeah? So it's fine to focus on this special class. And because we then have planar triangulated graphs, we can know the exact numbers of edges and faces in these drawings. Yeah? So for example, we know that the maximal planar graphs have exactly 3n-6 edges and 2n-4 faces. So in order to see this algorithm, we go in 4 steps. So the first is we will look quickly at barycentric representations of graphs. So this is just a way of defining the coordinates of vertices. And then we do 2 things here, labeling angles of graphs and coloring the edges in different colors. So this is the magic that happens in the middle. And once we have that, we can obtain planar straight line drawings by using this information that we computed here in these barycentric representations. So what is a barycentric representation, or what are barycentric coordinates? These we use if we have 3 points, A, B, and C, in the plane that span a triangle, and we have a point inside that triangle. And now we can define coordinates of this point with respect to the 3 outer triangle corners. If we require that the point P is represented by a triple alpha, beta, gamma, and these values alpha, beta, gamma need to sum to 1, and then the point actually has the coordinates that we go alpha times A, beta times B, and gamma times C. So this would be the barycentric coordinates. And if we see what that means, if we have our triangle and P is somewhere inside, then you can see this as a plane in the 3 space that is spanned by the 3 corners A, B, and C, all forming their axis, their coordinate axis. And this is exactly the plane that forms this alpha plus beta plus gamma as 1. And now so the alpha coordinate gives how far we go from A. So you can see this as a plane that is orthogonal to the x-axis, the first axis. And this intersects our great triangle in this particular line. So all points on that line have the same alpha coordinate. And if you do this for all three coordinates, you see that beta is constant here. And we already have the unique intersection point. But if we also add gamma, then this also passes through the same point. So why are they useful? Well, we can use them for a barycentric representation of a graph. So this barycentric representation is now mapping all the vertices of a graph to these triples in barycentric coordinates, and they will be then placed inside some triangle that is spanned by three corners. So what we need now is an injective map that maps every vertex to such a triple so that the properties are satisfied, namely that the sum of all coordinates is 1. And then, and of course, all the coordinates are between 0 and 1, so we cannot have any negative values. And additionally, the constraint is that for every edge of the graph and any third vertex, let me see, maybe I draw this. So if you have some edge uv and some vertex x, then the second condition says for every such edge and every vertex that has a different point, there exists at least one of the three dimensions k in such a way that the position of x, or the coordinate of x in that dimension is strictly larger than the position of u and v. Okay, so for example, if we take, I think this was the beta direction, so we would have a separating line between x and these two endpoints of the edge. So it will become clear why this is a useful property. So what do they mean? The first one is clear. This kind of maps the point into a triangle, and implicitly we have the three corner points on unit distance from the origin. But the second condition is now what becomes interesting. So we have the edge uv, and we require that we have three options of placing k. So if k is 1, the first dimension, this property would mean that x needs to lie in this pink area here. Or it can be in the second dimension, or it can be in the third dimension. So second dimension was the example we had before, so it can be on that side of the triangle, or it can be above that. But x cannot lie inside this white small triangle. And this is maybe a property that is helpful for planarity, because we have some kind of restricted region here that cannot be, at least there cannot be a point in there. So we call this also the forbidden triangle because nothing can be placed here, and we will see how this actually helps. So there's one variation of this barycentric representation, which we call a weak barycentric representation. Now it's important to focus on the differences. The first condition is the same. The second condition also says that there must be one of the three dimensions where something happens. But now we somehow relax a little bit this requirement of being strictly larger in one of the three dimensions in order to go to kind of a lexicographic sense. So we can say either the first is true, so x is strictly greater than u and v, or it can be on the same coordinate, but then if you go modulo 3, then in the next dimension we need to be strictly larger. So you can still lie on the line, but then in the next dimension it must be greater. So this still means that if you go back here, no point can be on an edge of that forbidden triangle. But you can be on that edge, but then you need to be somewhere here. So basically the argument is very similar, but this gives us a tighter bound for the drawing area later. Okay, so what we are interested now is using this barycentric representation for getting planar drawings of graphs. So the first lemma here states that if we have a barycentric representation of a graph satisfying the two properties that we had before, then we can find a mapping that actually puts every vertex to a point given by these coordinates. Yeah? So you go, you have the three coordinates v1, v2, v3, and you have the three endpoints which are at unit distance from the origin. Then this gives a location for the vertex in the plane, and this actually gives a planar straight line drawing inside this triangle spanned by ABC. So let's see why this is true. First of all, we have this property with the forbidden triangles. Yeah? So clearly there can be no vertices inside here, which is already a kind of goes towards the direction, but we want to avoid any edge crossings. So the question now is, can it happen that two edges uv and xy cross if we have such a barycentric representation? Yeah, so two edges crossing, meaning that we have four vertices, and in some way these two forbidden triangles need to intersect. Of course, on its own, it's totally fine if some vertex x is placed here, and it's totally fine that some vertex y is placed here. But of course, because this is also an edge, the same property needs to hold for u and v, and we will see how that gives a contradiction. So the answer is no, this cannot happen, but why? Yeah, so what we need to do is that for each edge, the property that we had for barycentric representation needs to hold. This means that there must be some dimension where, for example, the coordinates of x are strictly larger than the endpoints of the edge uv in that dimension, and in some other dimension, can be a different one, the coordinates of y, so the other endpoint of the second edge, needs to be strictly larger than u and v. But now we flip the roles of uv and xy, so the same is true here. So u needs to be strictly larger in some dimension than x and y, and v needs to be larger in some dimension than x and y. So now we have basically four dimensions possible here, but of course we have only three dimensions in total. Yeah? So this means that some dimension needs to be used twice. Yeah? And also what is immediately clear is that these dimensions need to be different, because otherwise you have the contradiction immediately. Yeah? So if I and k would be the same, this xi cannot be larger than ui, and ui can be larger than xi at the same time. Yeah? So these need to be disjoint, these two sets, and one of these two sets is actually a single dimension. Otherwise it cannot work. So for example, assume without loss of generality that I and j are the same. For example, they are both 2. And what this means is that x and y are in the same dimension strictly larger than u and v. And this means we have found a separating line that separates the two edges in that dimension. Okay? And this is what we need to guarantee that the edges cannot cross. And of course, if you play a different role or flip k and l, then the same is true. Okay? So this is the property, this forbidden triangle property, that tells us if we find a barycentric representation of a graph, then it will be crossing free.
What was the weak barycentric representation?
You can do exactly the same argument. Yeah. The only thing is that now what can happen is that x is on the line supported by one edge of the triangle, but it needs to be in the second dimension here. Yeah, so it could touch that, but outside of the forbidden region. Yeah, so this variation basically gives the same statement for weak barycentric. Yeah. Okay, so what do we need to apply these lemmas for our purpose? We need to find a good way of computing barycentric coordinates of points. And then when we can prove that the properties are satisfied, then this lemma tells us that the resulting drawing is plane. Okay, so now we go towards computing the barycentric coordinates. The first thing is the so-called Schneider labeling. And what this is the following definition. So if you have a plane triangulated graph, so this type of graph that we use here, then we want to label all internal angles with 3 numbers or 3 colors, 1, 2, 3, such that 2 conditions are satisfied. The first one is the face condition. So every triangle contains all three labels 1, 2, and 3 in counterclockwise order. Yeah, so I can label this angle 1, 2, and 3 counterclockwise. I could also put 1 here, 2 here, and 3 here, and so on. So this needs to be true. That's the face condition. And the second condition is the vertex condition, which says that around each internal vertex, these three labels 1, 2, 3 form non-empty contiguous intervals in counterclockwise order. So you have at least one angle with label 1, but possibly many more, but they form a contiguous block. Then you go to at least 1, 2, possibly more, and at least 1, 3 or more. So these are the two conditions for a Schneider labeling of a planar triangulated graph, and of course we need to show that this thing actually exists. Yeah, this is an example. We can simply try to fill this, okay? Just to understand the properties that we want here.
Excuse me.
Yes.
Is it related to the Sperner lemma? Explain. I mean, maybe in the proof there are some similarities.
Yes, maybe. I'm not very well aware of the proof of Sperner's lemma, but maybe you see some connection and we can talk about it. So what is usually done is that you put the same label. You start with some corner and put the same label, and then if we just follow the properties, we want 1, 2, 3 counterclockwise in every triangle. So this implies that here we need 2 and 3, and in the same triangle we want 2 and 3 here, and 2 and 3 here, and then you can start filling this entire triangle basically by following local conditions, trying to, at least in this example, see that a Schneider labeling exists. Okay, but in order to show that this always works, we can basically compress the graph into some triangle and then one by one insert edges and extend the labeling. So the way to do this is to have an edge contraction operation that helps us to bring the graph down to a triangle. And what this simply does is you take an edge, you remove that edge and unify the two vertices. So their two neighborhoods are basically joined afterwards. And now we can say some edges in our graph are contractible if they satisfy a certain property. Namely, if we want to contract an edge UV, we need that UV have exactly two common neighbors. In this example, this is a common neighbor of U and V, and this is a common neighbor of U and V, and that's all. And in that sense, we can take that edge, pinch it together, and the resulting drawing that you get here is again a plane triangulated graph. So the property here is that edges are contractible if and only if they are not part of some separating triangle. Okay, a separating triangle is a triangle that forms a cycle in the graph, and you have stuff inside and outside. And if you try to contract an edge UV that is part of a separating triangle, then something strange will happen. Yeah? Namely, if you look at the common neighbors of U and V, there's one here, there's one here, there's one here. So this does not satisfy the property here. And if you would try to contract this, of course you can do and merge the neighborhood, but then you would end up with a graph that is no longer a planar triangulated graph. Yeah, so we have to be careful with edges that are part of separating triangles, but all the others are fine. Okay, so we actually need to show this lemma, stating that if we have this plane triangulated graph with at least 4 vertices, 3 of them on the outer face, then we always find a neighbor x of one of the corners A, so that we contract the edge AX. And if we have this existence of such an edge, we can actually recursively apply the same idea. So the proof that we can do here is actually using induction based on n. Maybe I can quickly sketch the ideas that are going on here. So you would start this induction with the base case n equals 4. So what is a plane triangulated graph with 4 vertices? Well, is exactly K4. Okay. And now one of the corners is A, for example this one, and then we find the center point X, and the edge AX is of course contractible. Yeah, so this is totally fine. And if n is larger than 4, there's two cases. The first one is we have our outer face A, B, and C, and we find some kind of neighbor X of A that is actually contractible. If it is contractible, what does it mean? They have exactly two common neighbors, like this. And the rest of the graph lives here. Then we have this edge, we can contract it, and we're happy. Yeah? So the second case is maybe the one where we assume this is not true. So our edge AX is not contractible. So what does it mean that an edge is not contractible? We know that then it must be part of a separating triangle. So we have our big outer face, ABC, and now maybe some X here, and inside this we might have more things, for example like this. And then we have a separating triangle that we find here. And then we cannot easily contract this edge AX. But now we want to do this using induction. Maybe you already see how we can apply induction now, because we have this separating triangle. And of course this is a smaller graph with that property. Yeah, so we can apply induction on the graph that is spanned by A, X, and C. Because induction hypothesis is true, we know that inside this triangle AXC, A has a neighbor with a contractible edge. Yeah, so for example this vertex here, and then we simply use the same. So this means that we can always find an edge even adjacent to one of the three outer corners that we can contract, and if we apply these contractions we end up with a triangle in the end.
Isn't it the case that
Yes.
you somehow enumerate all of the edges connected to A from the cluster?
Yes.
Like the first one is the one which is contracted. Isn't it the case also?
Yes, because inside here you cannot put a separating triangle.
I mean,
That's even easier algorithmically to find this edge. No. You could show that if you take a specific neighbor of A, then it also is always contractible. Okay, so from this we want to show that now every plane triangulated graph has actually such a Schnieder labeling, and again the proof uses this kind of contraction lemma and also works on induction. So if we have an outer vertex A, we want to show that there is a Schnieder labeling with all angles actually having the property that all the angles have label 1 at A, so the one that we wanted to construct. So obviously if you have n equals 3, so just a triangle, then this exists. It's a single triangle and you can choose to label the angle at A with 1. So now let's use a graph that is larger, and we know from the lemma that AX is a contractible edge, which always exists. Okay. Then what we can do is, by the induction idea, to do a Schnieder labeling for the graph where we have contracted this edge AX. Yeah, so this is this graph, and by induction hypothesis we know that such a labeling exists here. And now we want to extend this labeling to a labeling that is always the same out on the outer part, only inside this blue region we can kind of modify the labels. So if we look at the labeling, then all of those angles are labeled 1 necessarily. And then we had this triangle condition that if you go counterclockwise, then every triangle is 1, 2, 3. Yeah, so this implies that all the other angles need to be 2, 3 here, 2 here, 3 here, 2 here, and 3 here. And now we need to extend this labeling somehow to be correct also with the inclusion of the vertex x. And of course you keep the labels 1 here, and we also want to keep the labels 2, 3 here, and 2, 3 here. And now this is basically the new part. And the way to do this is now to look at the angles that we had here, and now we introduce some new edges that connect to the new guy x. But we make sure that these angles all keep the same label 3. So this will be a 3 and this will be a 3. And likewise we do on the lower part here around this vertex, which had the label 2, and now we make sure that it keeps the label 2. And this is also locally consistent with all the other triangles. And now the thing that that happens finally is that if you take the labels on that part that is marked green, so all the triangles that are not adjacent to A, these still need a missing one to complete the triangles. And because they are consecutive, that also satisfies the vertex property. Yeah, so we put the label 1 in all of those. And finally, the other edges here, they will get on the one side like the label 2, and on the other side the label 3, just to complete the missing angles. And this is a way of extending locally an existing valid Schneider labeling to one that is also valid on that part. Okay, so as far as that, we have our plane triangulated graph, and now we have a labeling on all the angles that is satisfying two properties on triangles and vertices.
So eventually we use this Schneider labeling in order to find some barycenter reference?
Yes, exactly. So the next step is that from this labeling of the vertices, we can now obtain a coloring and the direction of edges, which is called a Schneider realizer. And the way of doing this is we have now all the angles, and we want to obtain edge orientations and labelings for the graph G. And what we know is that all the triangles have this 1, 2, 3 property. So if you have two angles 2 and 3, because of their local triangle conditions, you know that if you follow from this 2, 3 label to the other side, they both need the label 1. Okay? And if we use for 1 the color red, for 2 the color green, and for 3 blue, then we can color that edge a red edge, and we orient it to the two angles that have the red color. And what happens if you look at a particular vertex, from this mapping we know that whenever you have an edge that has the same colored angles on both sides, it's an incoming edge. So you have 2 red incoming edges here, 2 incoming green edges, and no incoming blue edge. And those edges that are between 2 colors, they are outgoing. And there are exactly 3 outgoing edges, and 1 in each color, by the properties of the Schneider labeling. Okay, so we can now define a Schneider realizer by doing exactly that. So we take a plane triangulated graph, and we orient the edge set into 3, or we color them and orient them, and we obtain 3 sets, T1, T2, and T3. And then for each internal vertex, it is true that it has out degree 1 in each color. So there's exactly 1 outgoing red, green, and blue edge. And if you look at the counterclockwise order of edges around the vertex, then it needs to be like that. So we have, if you just go, then we have outgoing blue, incoming green, outgoing red, incoming blue, can be empty, outgoing green, incoming red, and outgoing blue again. So this is always the case. Now we know that every plane triangulated graph has such a Schneider labeling, And then we can do this mapping, so it also has a Schneider realizer. Going from the labeling to the realizer is a very trivial step, basically.
Is there any way that we get some Schneider realizer without using, I mean, is there any one-to-one correspondence between these realizers?
Yes, there's one-to-one correspondence. So if you have the edge coloring and direction, you can go back to the labeling. Yeah, but the labeling is basically algorithmically somewhat easier to get. But if you have some way of getting this orientation immediately, you can use it. But now let's look at some properties of these Schneider realizers. So if we use the coloring from the labeling, what we get is this kind of edges that we have here. Okay, we know all the inner edges that are coming in here have the same color, because we started putting all the labels 1 here, all the labels 2 here, and all the labels 3 here. So this means they all come in, and the outer face is somewhat special. So the 3 black edges, we don't put any colors. So what is also true is that for every vertex there exists one outgoing red, one outgoing green, one outgoing blue. But of course, if you follow that edge, the same property is still true. So you can follow red outgoing edges from your starting vertex, and you will end up in the corner point. Yeah, so there exist red, green, and blue paths from every vertex going to A, B, and C. This is basically the sink of these paths, or the root of the tree that will actually occur here. Yeah, so actually every set of edges Ti is a tree on all the inner vertices and one of the outer vertices. The outer vertex is the root, and this gives us a directed tree. And basically we partition all the edges of the graph into 3 colored directed trees that cover all the edges except the 3 outer ones. What you can also show is that for each vertex v, if you have the 3 paths, to the red path, the green path, and the blue path, these 3 paths cannot intersect except at the starting point v. We don't have the time to actually show the proof of this, but it's not. You can try by contradiction, but this cannot happen. So if this property is true, what we can do is we can define the 3 paths: the red path going from V to the red corner, the green path going to the green corner, and the blue path going to the blue corner. And this separates our triangle, all the faces of this graph, into 3 regions. So we have a blue region that we call R3, a green region R2, and a red region R1. And this will be useful for getting the barycentric coordinates later. So if we have 2 distinct inner vertices of a planar triangulated graph, then the following property is true. If we take V and we have 3 regions, and now the vertex U must be in one of the 3. Okay, so let's assume it's in region Ri, and then the lemma claims that the subregion spanned by the 3 paths going from this vertex U is actually a subregion of Ri of V. Now what does it mean? We take V, and for example U is here. I think the regions are defined that if U is on that path, on the red path, it still belongs to the blue region. If it's on the blue path, it belongs to the green region, and if it's on the green path, it belongs here. So what we now know is that from U, the property holds that there is some directed path to A and some directed path to B. And of course some blue path here. But this means if we span the 3 regions from U, then we are actually in a proper subregion with respect to the parent region. And this means that if we maybe count faces here, this would give distinct values for every vertex. Okay, so let's now define this face count and the vertex count, and this will be what we need for the coordinates. So for each of the 3 regions, let fi of v be the number of faces found in that region. That's clear, and all the faces trivially need to sum up to 2n minus 5. Why minus 5? Because the outer face we don't count. And we know there's in total 2n minus 4 faces, but the inner faces are 2n minus 5. And if you if you partition them like that, you will end up with that sum. Or you can alternatively count the number of vertices in each region, including, so you exclude one of the paths. Yeah, so when you count vertices, like I said, then it's everything in R3 and those on the red path, but not the vertex V itself. Just to make this maybe more clear. If this is the blue region, then we count anything in here for eta. And this means if you sum up all these eta values, you end up with the number of vertices minus 1, because the vertex V we don't count. Yeah? And that way we cover all the vertices. And now these are two ways of obtaining our barycentric coordinates now. How do we do that? Well, the first thing is to use the phase count metrics to define coordinates. So we simply say that if we have a vertex, then we do these phase counts for the three colors, 1, 2, and 3, and we divide this by 2n minus 5. We know that the sum of these f values sums up to 2n minus 5. So if we divide by 2n minus 5, we know that it sums to 1, what we needed for barycentric coordinates. And the claim is that this is actually a barycentric representation now. Okay, so for the proof, the first part was easy. If you add v1 plus v2 plus v3, we end up with 2n minus 5. So this is correct. And for the second part, what we need to show is that if we have an edge uv and some vertex x that is not part of uv, we needed this property for a strong barycentric representation that the coordinate of x in at least one dimension is strictly larger than those of u and v. This was the second property of barycentric representation. And the way to show this is that if we take this vertex x and we find the three paths to the three corners, then this edge uv will lie in one of the three regions, the two vertices. So for example, this could be u and v. But now we had this property shown a couple of minutes ago that if something is inside a region, then in this particular coordinate counting phases here, these two values are strictly less, or the regions are strict subregions, so the number of phases are strictly less than the number of phases with respect to x. Yeah, so in this particular example, this would mean that the region in some dimension of u is a subset of Ri x and also Ri of v is a subset of Ri x. And this implies that fi of u and fi of v are strictly less than fi of x. So also the second property holds if we use this for barycentric coordinates. So now what we need to do is, to get a planar drawing now, is to put three triangle corners. A, we put 2n minus 5, 0, 0. B, 2 is 0, 2n minus 5, 0. And C, we just put at the origin. And then when we do these coordinates in this triangle, basically what we get is a planar projection that we can map to a 2n minus 5 times 2n minus 5 grid. Yeah? Because these are the corners, and we know that all the counts that we did here are actually integers. Yeah, so the coordinates that you get are integer coordinates, so we live on the integer grid of that size. If you play the same game for the weak barycentric representation, the arguments are just slightly different, but now you can divide by n minus 1 because it's the vertex count, and then the same idea gives you an n minus 1 times n minus 1 grid. And this was the property that we wanted to have for like the smaller grid. Okay. So use actually the same idea, and yeah, we have n minus 1 rows, and if you measure the size by unit length, then it's n minus 2 by n minus 2. Okay, so basically that concludes the way of getting a planar, small, compact, straight line drawing of a triangulated graph using the Schneider method. If it goes about algorithmic running times and properties, then the labeling you can get in linear time by using this contraction sequence in reverse order. And obtaining that is nothing that is very complicated to do. The realizer is immediately clear. If you have the labeling going to the realizer, you just iterate through the edges. And for the barycentric representation, the tricky part is maybe doing these counts efficiently. So we need the eta values or the f values basically in linear time overall, but you can do this by traversing the trees in the proper order. So if you follow the literature, you can see the full proof of this running time. And this basically gives us the final result that we have this straight line planar drawing on this grid size, and we can even compute it in linear time. Okay. And that was the result of Schneider from 1990. On that slide, I just give you a bit of further reading references here. So Schneider's paper appeared in Soda, I think in the first Soda actually, and there's an entire textbook on planar graph drawing by Nishizeki and Raman, and there's chapter 4.3 basically describes this particular method. If you're more generally interested, and that holds for many of the lectures, then the first textbook is quite old now, but it contains many of the classic algorithms, and then the newer handbook contains more up-to-date material. Okay, so I'm almost done with my 1 hour, but maybe just also as a teaser for the afternoon, I want to conclude with maybe some open research questions here. And an interesting thing, if you want to get into graph drawing, is to maybe also look at the annual graph drawing contest that is held with the graph drawing conference every year. And what they do is they post, I think every 2 years they change the topic, post a problem, and people can submit solutions or program algorithms that solve these problems and then participate in the contest. And the interesting thing maybe even for this audience is that you don't need to attend the conference to take part in the contest. So you can do offline participation by contacting the contest chairs and saying you want to take part in the contest remotely, and that's totally fine. So there's 2 parts of the contest. The first one is this creative contest here, where they provide you 2 real-world graphs, and you can use your artistic skills and graph drawing skills to generate drawings, hand them in, and they will be judged by aesthetic value and how clear the information of the graph is presented. This year I think there's 2 graphs that they have. One is about characters in a movie and how they co-occur in movies, for example. And the second one is from cooking. So you have recipes and you have ingredients, and there's the graph of how different ingredients take part in different recipes, yeah, for example. But maybe what's more an algorithmic challenge is this live challenge, where they want to do crossing minimization of so-called upward drawings of directed acyclic graphs on a grid of fixed size. So you need to live with the space that you have. And this is judged by the number of crossings. So for example, this could be an input for that challenge. And a perfect output would be that one, which is even crossing free. Yeah? And upward means that you have a directed graph, and the y-coordinates of the target node need to be strictly larger than the y-coordinates of the source node. And the task here is to design and implement an algorithm to do that. But of course, to make this contest interesting and challenging, this is an NP-complete problem doing testing whether such a drawing exists at all. Okay?
Do the contestants need to somehow provide some tools for the algorithm or somehow?
No, it's like a coding challenge. Yeah? So different algorithms compete against each other, and the one that has the fewest crossings get most points in that category, and they maybe give you 10 graphs. And these graphs, I mean, for the automatic contest could be maybe a few thousand vertices. And you have 1 hour of time. So you need to, I don't know, do some heuristics, maybe some small subgraphs, you know exactly how to do it. Use creativity. Yeah.
What is the price?
The price is, it depends, but usually there's maybe a award money like €300 or dollars for that, and you get a certificate and of course, eternal fame because they have this list of winners from the last years. So it's and also it's a lot of fun to do this. Yeah. And maybe a non-contest related question to graph drawing, one that I like a lot right now, is to look at so-called mixed linear layouts of graphs, where you have a graph, even actually a bipartite planar graph here, and you ask whether such a type of layout always exists for these graphs, where you have basically the vertices all on a horizontal line, and now you need to decide to put edges either above or below. But the way of doing this in a mixed way is that one page is a so-called stack page, and here no two edges may cross. And the other page is a so-called queue page, where no two edges may nest. Okay? So it's forbidden to, for example, flip this edge here to the bottom, because then this long edge and this short edge would be nested. And that's forbidden. And this is an open challenge. Yes? So PuppyRef in 2017 posted this as an open problem, and it's not so easy to do this. All of this is related to a larger family of graph layouts of that type, where you have linear vertex order and then some number of pages where you can put the edges. And you can either ask, okay, how many stack pages do I need to show a particular graph, or how many queue pages, or now the new part is how to combine this. Yeah? So for example, a long-standing open conjecture by Yannakakis is that every planar graph has an embedding of that type with 3 stacks, so 3 planar pages. It's known that 4 always works, but the conjecture is 3. So the book embedding conjecture for planar graphs. So it's known that 4 pages is always sufficient, but no graph is known that needs 4 pages. So far, all planar graphs could be mapped on 3 pages, and Yannakakis conjectured that, but there's no proof. But that's a tricky problem. Maybe not something you would give your master students. Okay, and with that, I want to close this first morning lecture.
We may have time for 1 or 2 questions.
Of course, not a question, a comment.
Yes.
I asked you about this Spencer lemma. It seems that it is some kind of vertex angle dual. In the Spencer lemma, which is related to Higgs game, you put one, for example, a triangle. Of course, it is also generalized to simplicial complex. You put 1, 2, 3, and then between 1 and 2, you just put the sequence of 1 and 2, and something like that. And it seems that you nearly do the same, but for angles.
Okay.
So there is, the Higgs game has contests, because the similar game, which is Bridget by Shannon, Claude Shannon, is P polynomial time, but this one is NP complete.
Okay.
So the contest is the people starting to play this. So I think it is nice that you mentioned that the same contest is for the angular one, and this is very interesting for me.
Yeah, thanks for the connection. I mean, I'm not an expert in these areas, but it's good to...
It is the dual.
Yes.
You are going from vertex to angle.
Yes.
And similarly doing the same idea. Thank you.
Okay, nice. Thank you.
Any other questions? Okay, so we have 30 minutes coffee break in the other room, and then we'll be back with